3.1 example 2 is a really important concept in math, which is the idea of, how do I go from a graph to a function? And with vertex form, it's actually not as bad as you might think. All we need, and I'm going to write it out here, is we need to know where the vertex is, and then we need to know a point, and I'm going to put here that it cannot be the vertex. So a point other than vertex. And the logic behind that is that once we know the vertex, we are going to know what P and Q are. Let me put vertex form up here again. So I equals A times X minus P squared plus Q. So once we know the vertex, we know what P and Q are, but it's really important that whatever the value of A is, doesn't change where the vertex is, right? It can change if it opens up or down or so on. But once we know the vertex, we know P and Q, any other point on the graph is going to give me a value of X and Y that the function has to work for or has to be satisfied for. So if I know what P and Q are, and I plug in a value for X and Y, A is the only unknown, and therefore we can solve for it, and that gives us the equation of our function. So what we're gonna do in these examples, and I'm gonna do them both on one page, is we're gonna first look at the graph, and they typically put these little dots to indicate that it's perfectly at that point. And I can see on this graph that my vertex is at the point 5, -4. Now, be careful with the graphs. You have to make sure you read the scale carefully. Both of these graphs, sorry, not both these graphs. The first graph is 1-to-1. The second graph, each of these ticks actually represent 1/2. So this is 0.5 right here, 1.5, 2.5, and so on. You have to be really careful you're reading that scale correctly. So if I know that my vertex is at 5, -4, I know that P is equal to 5 and Q is equal to -4. The only other thing I'd like to be able to identify directly from the graph without doing any math is that we do know that because the parabola opens up, A must be greater than 0. And that's fine. The reality is that limits the answer, but not a lot. There's technically infinite numbers that are greater than 0. But if nothing else, it gives us a bit of a check and balance from when we're actually solving using an algebraic technique. So if I know what the vertex is, I'm going to put my function down here. Y is equal to A times X minus P squared plus Q. I'm going to substitute in the value of P and Q. I get that Y is equal to A times X minus 5 squared plus -4. And then what I'm going to do is I'm going to go back and look at my graph and find any other point on the graph that's not the vertex. I love to use the y-intercept when I can, but if the graph gives you, and I know it's kind of hard to tell on the YouTube file here, but they actually put a couple points right here and right here. So I could use the point 8, -1, or I could use the point 2, -1. The reality is that it does not matter. Both of those points on the function, both of those points are on the function, and neither of those points is the vertex. So they'll satisfy this technique, and it makes no difference which one you choose. That being said, I typically use the smaller numbers because they're easier to manipulate. So what I'm going to do is I'm going to substitute the point 2, -1. Remember that any point is an x, a y coordinate, which means that I can take the function I just had and I can put 2 in for x, -1 in for y. I would get that -1 is equal to A times 2 minus 5 squared minus 4. And A, I'm just going to move that down a little bit, it kind of bled into the other writing. A is now the only unknown. So what I'm going to do is I'm going to take this equation and I'm going to solve for A. There should only be one solution. So I'm going to say that -1 is equal to A times -3 squared minus 4. I'm going to add 4 to both sides. I get that +3 is equal to -3 squared is 9. So it's going to be 9A. When I divide by 9, I get that 3/9 or 1/3 is equal to A. Now, we said above that A had to be greater than 0, and we got that solution, so we're on the right track. The last step in this problem is to write the function itself, which is y equals 1/3 times x minus 5 squared minus 4. And that equation will give us the graph given to us in the question. And that raises, another way to verify this. If you're saying that this function in red at the bottom is representing this graph, you could use your calculator and check that. If you're going to use that technique, make sure you make your window settings the same as what's given to you. Otherwise, there's no reasonable expectation that it would look exactly the same. All right, we're going to do We're going to do B at the same time. I'll do it in blue to try to differentiate between the two. But we're going to do the exact same thing. I'm going to find the vertex. The vertex for this particular parabola is at 0, 3. Just looking at that y scale, it's 1 each tick. That lets me know that P is 0 and Q is +3. Worth mentioning as well that this parabola opens down, so we know that a must be less than 0. And while I'm at it, I'm going to identify a point, and it's got a really nice point to work with. I'm going to write here that this graph does go through the point 1, 1, and that's this one right here. Again, be very careful with the scale given to you. All right, so now we're going to take our vertex form, y equals a times x minus p squared plus q. I'm going to do p and q first, and then I'll do the point next. I'm going to have y equals a times x minus 0 squared plus 3. Let me clean that up a little bit, because that's y equals a times x squared plus 3. And then because it's going through the point 1, 1, that means I can substitute 1 in for x and 1 in for y, and I get that 1 is equal to a times 1 squared plus 3. I'm going to subtract that 3 from both sides, and I get that negative 2 is equal to a. Well, that meets what we expected. We expected a to be less than 0, so the last part is to write our function, which is y equals negative 2x squared plus 3. And that would yield the graph given to us in the question. All right, this type of math is very, very important. We do spend a lot of time in 20-1 and 30-1 trying to come up with an equation that will model whether it's a real life scenario given by a picture or most commonly some kind of a function given by its graph.